right, I think we will get started. There are people still coming in, but a few things before we get started. Use the URL for Slido, use the code. We are in room 6. So that would be really nice to get some questions. So we'll go through them at the end, I guess. So I want you to think about a system that you will be creating, or think of it as you will be creating. It's a very simple system, and I want you to create that thing from scratch. There are very few rules or like requirements to that system, and those are the following. So the system that you will be creating will be counting number of people going in and out of a room. So like room like this, for instance, counting people going in and out, or a corridor, people passing by, or something like that. The thing that has to be there is quite a lot of focus on privacy. So I don't want you to leak the identity and people and what people are passing by. So I just want the numbers. Okay, 1 person, 2, 3, 10, 100. That's it. It has to be performing really well. So it has to have a performing system. So handling 2 people or 100, it should be able to do both. It has to be quick. So I want the data whenever things happen, not the day after, not like later, but now-ish. And I want it to be quite relatively cheap to run. While you're thinking about this kind of system and how it can be implemented and stuff like that, we'll use a few minutes telling a few words about ourselves.
My name is Tannas. I have a background in robotics, currently working as a cloud engineer for University of Oslo, where we are building an open source cloud services for research and education sector in Norway. And in my spare time, I'm playing around with robots and sharing my knowledge with open source community.
And my name is Rustam. I work for a consultancy company in Norway as well called Computos. I work mostly with architecture, with mostly on the Java platform, mostly with also quite a lot with cloud lately. I work, whenever I'm not doing that, I'm also been spending a lot of time with the Java community in Norway. I've been leading Norwegian Java user group for a couple of years. Also been leading a conference called Java Zone for 3 years. So there's a lot of things, and I also run a few communities in Oslo, and I'm a Java champion and also a Google developer expert for cloud. So that's us. And let's go back to the problem at hand.
Yeah, I think that maybe we could solve our problem with IoT devices because they are cool, easy to set up, they are accessible, and we can connect them with different sensors. So we can just use them to count people on streaming. And the number of these devices is just growing so fast. Already by next year, there will be 4 devices for each person on Earth. So maybe one of those devices can solve our problem.
I think so. Well, that was actually our first thought. That was the same thing that we thought. And it was like, OK, we can do that. We can just use IoT for that. And today we want to share the experiences we had and things that we kind of had to go through while building this kind of hobby project that we have. And tell you about like things, well, to do and not to do things. And before we go any further in like those kind of experiences and everything, I want to show you a typical IoT stack, the one how we usually, at least how we see at that thing. On the bottom there is an IoT devices. Those are devices that are kind of being sold to you as smart devices that basically have a bunch of sensors and a little bit of network connectivity and just sending things back and forth. On top of that, there is a kind of a bit heavier level or layer, which is IoT Edge devices that offer a little bit more than those basic devices. On top of that, we'll be talking about fog and cloud, and we'll get back to that in a second. Since we'll be focusing, as you might have guessed from the title of this topic, we'll be focusing quite a bit on IoT Edge devices. We also decided to split those into like 3 subcategories. We're going to mention some stuff about software they run, like operating systems and stuff, hardware they run on, and also architecture, the things that kind of are part of that little thingy. We have a few here. I'm not sure if you can see them. Well, we'll show things a bit later on, but we have a few tiny little things blinking here and 2 bottles of water. What can possibly go wrong with this thing? But, okay, before we go any further, let's introduce IoT.
Yeah, what are IoT devices in general? The IoT devices, or the Internet of Things, you can say that it's a connection between our world and the digital world. So these devices have internet connectivity. They generate and collect massive amount of data and send those data to the cloud or data center for processing, and then receive the data. And this is great, but there are some challenges as well, because as internet connectivity is just expanding and mobile technology is growing so fast, our lives become more and more dependent on such devices. And so as the number of these devices just growing so fast, the security challenges and privacy concerns that can affect our individual rights will also arise. However, we can say that these devices are great because they give more access and opportunity to more people.
And since we're talking about the number of devices growing and everything, the most obvious thing to do is to show you some graphs, right? Well, this one is very informative. It's the number of devices is growing, period. But, well, okay, I have another one that is a bit, I like a bit better. This one is actually pretty cool because it compares the growth of devices, different devices. So on the bottom there, the lowest, this tiniest little kind of thing in blue there, it is a number of PCs. So you can actually see it. It's slightly going down even. And then you have smartphones, you have smart TVs, smart home devices, all those kind of things. But still, I mean, nothing growing as fast as the number of IoT devices. That's the kind of the highest gray area up there on the graph. And that is actually quite an interesting thing because, like, well, everything is getting more of everything, but, well, IoT devices. Obviously, the regular IoT devices, as we know them, they have some advantages and disadvantages, right? So since those devices are very available, they are very specialized in doing things they're supposed to do, which is a very few things. It's not like general purpose device. It's just doing one thing or very few things at a time. So they are efficient at what they're doing. They are obviously quite fast at what they're doing. So the time processing things is quite low compared to like a general device. I mean, it's like you wouldn't put a laptop next to your plant to measure whether it needs to be watered or not. You would put a tiny little thing that will be using, I don't know, a thousandth part of the power and will be still faster and stuff like that, right? Most of them are mobile. They are because they're small. They also offer you some kind of tracking possibilities and also things like gyroscopes and GPSs and all those things, so you can add tracking and stuff like that. They're also, since they're being produced in so many big quantities, they're also quite cost efficient. So far so good, right? Well,
yeah, not everything is good. As I mentioned earlier, security can be a challenge because now we are talking about much more devices, and there are more devices, more formats and protocols to communicate through, and then we have more software and hardware that we need to update, operate, and monitor. Privacy can also be an issue because in most of the cases we send raw data over the network to servers, and both servers and network can leak data. We are talking about massive amount of data, and those data need storage and computing power that can cost a lot if we're running on a cloud. And environment, because we have to think about environment because we are creating now lots of hardware, so we have to think how we can recycle them. And as we are talking about many devices, those devices need to interact with each other, and that can be complex. And these devices are dependent on internet. So in most of the cases, if we don't have internet connectivity, so we cannot use them.
Yes, and well, now let's talk about IoT Edge devices. So, right, you have we kind of defined IoT. Well, that's what it is. IoT Edge devices are a bit smarter. So those are devices have a little bit of power, a little bit of processing power on top of that. Because, like, for example, thing I have on my wrist here is I would define it as an IoT Edge device because it's not sending my heart rate or anything immediately to my phone and just like, oh, hey, I got a heartbeat, oh, another one, and another one. And that would normally an IoT device do. This one would collect and count and everything and just send it whenever the phone would ask or whatever the rules are for syncing stuff, right? So if you have to tell like what is an edge computing in like one word, you would say, well, it's something that is there for improving operations and cutting costs. And well, I guess let's explain why and how that works.
Yeah, talking about edge computing, so we need to have a definition for that. As IDC says, edge computing is a mesh network of micro data centers that process or store critical data locally and push it to a central data center or cloud. So edge computing actually allows the data produced by IoT devices to be processed locally instead of sending across the network to a server or a cloud. So IoT computing typically collect data and sending somewhere else for processing, while edge computing keep most of the data on the device and do most of the processing locally. And then it will reduce the traffic, and you can say that it's much more secure. But it means that these devices have their own compute network and storage on the device, just in a smaller factor.
Exactly. So, and the thing is, before we go any further, I want you to remember one little thing. A mesh network of micro data centers. Just hold on to that thought for a little bit, and we'll get back to that in a few slides. But a mesh network of micro data centers. Okay. Since we mentioned like advantages and disadvantages for general IoT stuff, it's about time to say something about edge computing. So obviously edge computing is trying to address some of the disadvantages that we mentioned earlier for regular kind of dumb smart devices. Things like low latency is a thing because, well, you're processing things on the device. You don't have to ship data about your flower pot thing and humidity inside that the ground there to a server, do some kind of calculations and send it back to your phone or something. You can do it on your device. It also only can, be very privacy efficient because if and only if you do it right and you handle the data in the right way, it will give you a good privacy as well, because then you don't have to handle the sensitive data somewhere on the cloud or ship it over, but you can actually do all that on the device, remove as much as unnecessary unnecessary private data before sending it over. Like in our case, identity of people. You just remove all that. You just count people. You just say, well, 3, 4, 5, and just ship that over. Most of us would be definitely much more comfortable with knowing that, well, this camera is just sending numbers, no faces, no nothing. Very nice. Obviously, also, since you're not shipping data back and forth, you will also get a real-time availability. You will get a real-time data transmission, or very close to real-time. And in general, it will give you some kind of productivity increase. Because sometimes, in quite a few cases, it's not just about a nice to have, well, I mean, I don't have to send data back and forth. It's about that you are not actually able to send. I mean, if you're doing like license plate recognition on the cars going in and out of a parking lot, somewhere deep in a basement without proper decent internet connectivity, how do you send all those images to be processed in the cloud? You can't, right? Sometimes you're generating so much data that you cannot even send it over to the cloud because you will end up DDoSing your servers, or it will be super expensive to run a huge thing backend to receive all that data. But
there are some disadvantages here as well.
Ha.
So in most of the cases when we are talking about edge computing, we are talking about one device, and there is no redundancy. So it means that if our device fails, we need to replace it. But if something like this happens in the cloud, so we can just start a new virtual machine, or it can just automatically happen for us. It is risky because if we lose our device, we lose our data. And when it comes to security, so there are two different sides. On one side, we can say it is more secure because now it's less data in communication with the third parties, so it's better. But on the other side, we can say that it's less secure because the device itself can get attacked much more easier. So in designing such devices, we need to think about data encryption, access control, and the use of private network. And we have to make sure that our device is up to date every time.
Yep.
we use it.
So yeah, it's more like things to think about. It's not really like disadvantages or advantages for that case, but it's the things that to be kind of be aware of, right? So IoT versus IoT Edge. I want you all to think about your own homes. There is a big chance that you have some kind of smart assistant-like thing in your home. It could be like a a special hardware device that would do that, like Siri, Google Home, whatever. It could be a smart speaker. It could be just your phone with those assistants installed. But, well, you have something there, right? And also you have a bunch of some kind of IoT-enabled devices. So that plant, the pots or flower pots I was talking about might be one case. The other case, which is probably more likely, is that you will have some kind of smart lighting system that will do the controlling the lights, turning off and dimming and changing colors and stuff like that. So what will normally happen is that you're sitting on a sofa, you pull up your phone, you open an app, you press a button, and then the data will be sent to some kind of gateway, possibly even all the way to the cloud. We'll ask the clouds, like, hey, I have this data, what do you want to do? And then the cloud will tell the gateway what to do, and the gateway will tell to the lights to dim or change color or things like that, which is nice, and it happens so fast that you don't really think about it. Unless, well, there are some things that happen, right? Or you lose internet connectivity, or it can be some other things, right?
I don't know if you attended the keynote yesterday, but Hadi has some good examples of how these data can leak, how these devices can leak data. So, I mean, it is really great to use Home Assistant to turn on or off your lights, but you don't really need to share that information with the whole world when you're getting up, going to sleep, or when you're having party at home. So these devices can do most of the processing locally, instead of sending across the network.
I'm kind of thinking, every time you hear say that, I'm kind of thinking of the digital version of Home Alone movie, you know, the old one from back in the days. It's a digital version of that, turning on all of the lights, and then people are like, oh, the lights are off, now we can go and rob them. But, well, that's another story. But the thing is that if it was an IoT Edge device, it will be a bit more expensive to run, probably, because it will probably have a bit more hardware, a bit more processing power and stuff like that. But you can do all of those things. You can do like language processing, you can do analysis of things and everything on a tiny little device that is a slightly bit more powerful, probably a little bit more expensive, a little bit more electricity and power to run on. But this is a price to pay for things like privacy and things like not sharing these things. Because, well, most of those assistants have been in the news lately because they were sharing the data with some kind of third-party people, whatever. So, now that we know that IoT Edge device, let's go further to the connection between them. There are two things to know about. One of them is probably, just to check if your hands are working, clouds. Anyone have heard of clouds? Okay, yeah, hands are working, good. Anyone have heard of fog? Okay, yeah, that's what I usually see. That's what we've seen it most of the places. Like you say cloud, everybody's like, oh, yeah, I've heard that. And you say about fog, and then there's like, there will be like 3, 4, I think this is actually probably the biggest number of people raising hands. And there was like, I think 4 or 5 people. So fog is, well, we're not going to talk about cloud. Everybody knows what cloud is. But the fog is basically, long story short, everything that's yellow on that image. So that is a connection, network connectivity or local connection between devices. Remember the thing I told you about, network mesh of microdata servers? Well, those IoT Edge devices are kind of microdata servers. They can be implemented to to distribute the loads and to distribute the jobs to run in between. If one of them is too busy, it will send the data to another one and everything. And that happens through the fog, through some kind of network connectivity. So in addition to connecting devices, fog would also connect those devices to the cloud, or can do that anyway.
Yeah, just to sum up the difference between these terms. So we have edge computing, that it can be any devices such as Home Assistant, wearable devices, which refers to the computational process that we are doing on the device. The fog is talking about the network, so it's the connection that we need to send data from our device to its final destination, and the cloud or a data center can be someone else's computer. So that's how easy it is.
Yes, it's always somebody else's computer, the cloud. Okay, but so now we have IoT Edge. We kind of decided, okay, fine, we need a bit more processing power, so we'll go for IoT Edge. Now we had to look at software, hardware, and architecture, and things like that. And to do that, let's go back to our real-life example, the machine learning or AI, because it's cool, right? ML-based people counter, and our 4 rules, 4 requirements. Privacy concerns, so strict privacy policy, not leak data about people, perform well, low latency, low cost. Okay, so then
we had to find a hardware for that.
Yes.
Most of the cloud providers have their own hardware, such as Microsoft and Google, while AWS has a software that can be run on Arduino devices, such as ESP32. And there are some much more general devices, such as Raspberry Pi, Banana Pi, and Arduino, but they are not so specified for running AI on that.
And well, AI, I guess we should mention the AI part as well.
I'm thinking too.
We have a slide for that. Surprise, surprise. Who would have thought?
Edge computing, compared to the cloud, has much less resources and computational power. So running machine learning and deep learning on top of that will slow down the process. To bridge the gap between edge computing and cloud, some companies have already built some purpose-built accelerator devices. That's the way that these devices work, is that they have a chip that takes over the most expensive and heavy part of the calculation that will result in free, doing like the CPU free, and then we can use the CPU for something else. And this will speed up the process. But however, we cannot actually compare these like edge computing with cloud, because GPU is much more faster, but yeah.
Well, I mean, GPUs are bigger, faster. I mean, you can have GPUs on this as well, but there is this form factor and everything. So technically what you can do, you can make those IoT Edge devices grow bigger and faster and look kind of like monsters, or you can create more specialized chips on each of them. So the general CPU that will do all the general stuff, but then you can also create the specialized chips for that. And AI chips is one of them. And we had to look at a few devices that has this thing. It's usually called AI accelerators that are they're very good at one thing, and that thing is processing neural networks and stuff like that. So there are a few of them. There is one that we looked into or at was NVIDIA Jetson. It's a tiny little small computer-like thingy with a bunch of ports and stuff on it, and it runs a Linux-based distro. Nice. So another one was Intel Movidius and Myriad chips that looks like a overgrown USB stick from early 2000s. I don't know, probably more than just me had a stick like this that was 16 megabytes on and that size. So now this one can do neural networks instead. And it's very small, and it's just a USB stick. You just stick it into a laptop or Raspberry Pi or anything, and it will be able to take over the processing of the neural networks and stuff. Those are actually quite fun in one way, because you can plug several of them. You can just connect as many as you want. I think there is a limit, but and they will kind of work in parallel. Pretty cool. And then you have also Google Edge TPU. I'll explain what TPU stands for in a bit. And those come in 2 flavors. There is one that is very similar with the USB interface. The gray one that you see in the corner there. It comes with a USB cable, and you just plug it in. And the other one is the Google Edge Dev Board. And that one is a small computer that looks like this, where you have all the kind of connectors and everything, and it's running its own Linux-based, Debian-based distro called Mendel Linux, made also by Google. And there is also, so you have a fan and you have a heatsink, and underneath there you see a tiny little board. That's the board where most of the magic will happen. And the thing on the bottom there that is bigger is, well, kind of think of it as a motherboard in a way. It has connectors and stuff and power and things, but that's not the most important thing. The most important thing is that tiny little thing. And it is very small because, I mean, if you think of the size of that thing, that one you see there is a USB-C port. That's the one you have on most of your mobile phones nowadays, or micro USB port or something. It's the same size. So the form factor of that thing is very small, and I have this thing connected here. It's in a 3D printed box, so it looks a bit bigger than what it is. I'll lift it up in a bit because we have short cables. So on that little chip, you have a CPU, which is very similar to what you will find on a Raspberry Pi, or actually almost. If I remember it correctly, I think it is exactly the same one. And so ARM-based CPU. And then you have a TPU that is a size of, well, very small. That's compared to a penny. That's up there. You might have heard of TPUs before. Anyone? Yeah. Well, the ones you might have heard about, they usually look a bit bigger. That is the ones you will find on the cloud. So again, the difference of the performance and like the crunching power and everything is totally different. But the important thing is how much faster that tiny little device will get with this little extra chip. And we'll see, we have a demo there where we'll be switching between a CPU and TPU on the same algorithm, same video and everything, and we'll see how that actually behaves. Well, yes, so that one is a cloud TPU version 3, apparently, if you're judging from the sign. And that's a picture I took in San Francisco a few months ago, half a year ago, maybe, at Google Cloud Next, where they were like, oh, this is the new thing. So the sizes might differ, the processing power might differ, but it's not about like how powerful you can get. It's just like keeping the small factor and keeping the same kind of hardware, what you normally consider to be an IoT device, how much faster you can make by adding some specialized fun stuff to it.
Yeah, and here we have to talk about positive and negative-ish sides as well. So the price of this Google Crawl is quite okay. It's about $200, including camera. It has a okay hardware. It is as good as a Raspberry Pi 3. It has a low power consumption. It is small. It is based on Debian distro, which makes it more stable. And it has a chip specialized for running machine learning and TensorFlow Lite on top of that.
Yeah, and the thing is, so the point is, it's not to advertise, go buy this thing, because we're not working for that or anything. The point is, it's accessible. It's easy to get hold of, right?
Compared to other devices that we tried earlier, so it was much more easier to get a start with.
I mean, even I don't remember. I think even this one was a bit more expensive, and it was really hard to get started with, but well. Obviously, we tried to find some disadvantages as well. It was a bit hard, but one of the main disadvantages, I would say, is that the availability of software, because it's relatively new, it's still in beta. The community is not that like super huge just yet. It's going there, getting there, but it's not that big yet. You kind of feel that whenever you're having some weird errors because you did something wrong, really. It's your own fault, but you did something. You're trying to figure out what's wrong, and you Google for that, and you can't find anything. You ask on Stack Overflow, it's quiet. I just got, like, I think 2 days ago, an answer on the Stack Overflow question I asked sometime before summer. You know, so the community is not very big just yet, but it's getting there. It got much, much, much better since we started playing around with this thing. I think we started playing around with this just before Easter, so spring. And we did a lot of things. We did a lot of trying and failing, and we failed quite a lot, and we got to make it work also quite a bit. We trained models. We trained models on that thing. Actually, for Easter, we made it to recognize, to kind of differentiate between chicken, eggs, and bunnies. And everything else. So it would say, well, I think it's an egg. Well, I don't know what that is, but it's neither of those 3, and so on. So we just trained that thing on a very small amount of images, really. But it worked. And it was actually quite efficient in doing that. So it's cool. The thing is that the software availability might be a bit hard. We had another issue there where we were compiling a very big C++ library to for tracking. I'm not going to spoil what that is and everything, but we'll get back to that on our next slide. But the thing is, so we're compiling a huge library, and it took us. It would just stay there and swap and trash CPU. I don't know if you know what that is, but well, basically swapping and just killing the CPU performance at all. And would nothing happen. And we were like, what the heck is that? Is it just because of the hardware and everything? Then I tried to build the same thing on a Raspberry Pi on exactly the same hardware, exactly the same Debian-based Linux-ish. I mean, some different flavor, but still same. And it worked. I mean, it took like 2 hours, but it worked. And then we realized that, well, the C compiler libraries were old and outdated, a bit outdated, not much, but a bit. And that one had a bug that would cause this thing to fail. And then we were like, well, how do we update this? Because the sources are there pointing to Google, and Google is not updating that because it's probably dependencies to something else. So we did something that you're not supposed to do. Please don't do that. We did that so you don't have to. We actually put in the Debian sources into that and force upgraded all the packages. It worked. I don't know why it worked, but it worked. And we actually managed to compile this thing. But it's a very bad idea because it will probably, most likely, in most of the cases, it will break things. We were just a bit lucky that it didn't. So don't do that. But, OK, so now we have hardware. We know what it is. We know what we want.
Let's go back to our question.
And software.
Yeah. For people counter software implementation. So to understand that, we need to understand some machine learning terms such as classification, detection, and tracking. Classification is actually related to categorization when we know our object on an image and we understand what kind of object it is. That's it. In detection, we can see our object and now we know where it is on that image. And it is quite OK as well, but when it comes to tracking, tracking is quite similar to detection, but it's much more complicated because in tracking we have series of images. And in all those images, we need to find our object and we need to see where it is on that object, and we should keep tracking that. So in puppy language, so in the first picture, we can see that we have puppies and not kitties. In the detection, we know that we have a puppy and where it is. And the third picture is tracking. Now we have a series of frames, and our dogs start moving. So now we have to track our object from point A to B. That can make it very complicated.
And the important thing here is not just as you look at an image at a time and say, oh, it's a dog, it's a dog, it's a dog, it's a dog. You actually know which dog it is, and you know where it's been moving. So that's the difference. That's the tracking for you. But to explain you why detection and tracking is so hard, it is. We kind of have to go back a little bit in the history. So one slide of kind of going back to late 1800s, where this guy called Edward Maybridge was playing around with animations. So he was creating animations of animals and like things like that. So this horse thing is one of the very famous ones, where you might have seen it as like a round thing with all those images, and there is a camera pointing, and it's again spinning really fast, and you get this idea of the horse moving. So the point is that the video is a set of images. Video is ever since that time, late 1800s, it's been a set of images, just going faster after each other. So what varies, or what has been changing since that time, is the resolution of those images and how fast they change. And well, detection, running detection on a single image, also single frame, I mean, it's CPU expensive and stuff like that, but it's not that bad. You have machine learning algorithms. You have those special chips that can do very nicely well-performing algorithms and stuff like that to do all this kind of thing. So while it's kind of expensive-ish, but it's not a problem. We have a solution for that. Tracking, on the other hand, is a bit tricky because then now you have to look at a series of images and assign IDs to an object that you see and track that object movement through the series of images. So if we talk about the people counter example, or the project that we're playing around with, is that you say you have a 10 seconds video with two people moving, well, apparently towards each other, and we are filming at 30 frames per second. You will be sitting there with 300 images of those two people. If I ask I'm pretty sure that if I ask any of you in this room, there will be a very, very big chance that you will be able to count and tell me that there are 2 people. If I show you that 10-second video and ask how many people they are, you'll be like, yeah, well, that's 10, that's obvious. What else? I mean, why are you asking? But the thing is, computers don't do that. Computers don't know that. They just look at an image, it's like, oh, 2 people. And then next image, oh, 2 people. I don't know if it's the same 2 people, but I see 2 people. And then you have to actually do quite a lot. I mean, there are like libraries for that, and C++ library that we were building, compiling. It wasn't, I mean, it's out there, but we were compiling that to run, to use in our algorithm. To do that, it's actually quite expensive because it runs a lot on CPU, and you really want to free your CPU as well. And whenever the third person appears, you actually need to be able to assign a third ID to that person or an object, or depending on what you're looking at in an image, and then actually also see the direction and try to predict how it's going to be moving and if it is the same person or not. And you have to do that in a loop.
Yeah, and this is the process. We start with capturing a camera, and then we need to resize an image because our machine learning models use a specific size of images. And when we have done that, we can start running our machine learning processing models on top of that. When we have the result, we can just display it on the screen. And we do all those 4 main steps for each frame. And this is the system in action. So here you can see that we are running a model from a live video feed from our camera. Here we are using a person labor, so you can see how accurate it is. So we are much more human than the photo on Roshandel access card. And yeah, it is. Yeah, the inference time is 8 seconds for 120 frames per second. So it means that we are going actually through all those 4 main steps in just a few milliseconds. And we can say that it is really fast, actually.
It's actually really fast. But then the thing is that you're using a tiny small device that is able to do that. And this is kind of amazing. And I want to show you an example, the one that I promised you. It's a recording of exactly the same thing that we were trying to do and try to explain. I just cannot find the mouse. Oh yeah, there it is. Okay, so before I click play, what happens here is that we're doing exactly the same thing as we were doing with people. It's just cars. We actually tried to switch that to people and was able to find people inside cars and everything. That was quite fun, but that's another story. Cars are, we're counting cars. And now we're going to switch at some point. Up there, you'll see it says on CPU or on TPU. And you'll see the performance difference. And this is the thing I really want you to look at. So now we're running on TPU. Things are going quite fast, and we're doing quite a few frames per second. I cannot really see. Now we're back to CPU. So the Raspberry Pi CPU for you there, Pi 3. And we're back to TPU. And this is actually quite a big difference. I mean, it's a tiny little chip and tiny little thing, but the difference is amazing. So a few things that we learned when building this kind of thing before we go into like demo and code and stuff. Well, one of the things that I, to be honest, didn't really think about to begin with is that various machine learning models will have different performance. Well, I mean, I kind of thought about that, but I didn't really think it would have so much impact on what I'm doing. But whenever you're running that thing so many times a second, a tiny little difference in milliseconds of the algorithm that you're using, because there are many of them and they're like different and they're doing different things in performance, slightly bit different. You wouldn't care about that when you're running it on a huge data set and you can wait for an hour or, well, for you it doesn't matter if you have to wait for 2 more minutes or less, right? But when you're doing so many times a second, it will actually matter. So the performance, depending on different models that we tried, was from anything from 120 frames per second to around, I think, 80 or 60 or something like that. So things change, things vary. You can kill your performance simply by adding a few lines of code. I did that, so you don't have to. We had a demo 2 hours before the demo and presentation. It was a couple of weeks ago. Nothing worked. We went from 120 frames per second to 1 point something frames per second. So basically dead. And nothing happens and nothing works. And I'm like, oh God. I delete 3 lines of code, 2 print statements and one some kind of pandas, something, I don't remember, like playing around with arrays and stuff. And it's back to 120 frames per second. So you can kill your performance with a simple, well, I mean, everybody knows that print statements are very expensive. So things like that will kill your performance. So optimize, optimize, optimize is a thing. And also you need to think about like what kind of hardware, what kind of devices you really want, what do you want, what cloud you will be talking to lately and stuff like that. So I think we should show a little bit of code, because the point is to show you a bit how easy it is. I mean, we're not going to teach you like how to code that. You'll find that in documentation, but well.
Yeah, do you want to see some code?
Yeah,
Let's see.
Okay. That was a rhetorical question.
Yeah, as Rustam said, it is just to showing you how easy it is to get started with Google Coral. Here we have the main function, so here it's where we declare our variables for later use. In most of the cases are command line parameters. It's an initial script to just start capturing and displaying the results on the screen. Then note the inline function frame callback. It's an image processing steps. We are calling this function for running machine learning models. And then we have GStreamer, that is a library for supporting complex video streaming, which start actually all those 4 main processes here.
So it starts, it kind of runs through each frame, separates things by frame, calls a fallback function for each frame, and so on. And well, I don't really, this is a helper method. I don't really want to spend much time on this. But the thing is that, like, for example, I want to mention that it comes with a few libraries that are, I think they're open source. They're on GitHub and everything, so open. Well, I'm pretty sure they are. And it has lots of helper methods. So like, for example, this one has a threshold. You remember that thing with my access card that would count that as a third person in a room? Well, the thing is, if you adjust the threshold, and so you can remove all those false positives and everything, because you know that, okay, well, I need to be 80% certain that is a person or 90% certain, and so on.
And some more handy methods here are just for calculating the inference time and getting the model input size, and initializing the model. And we should maybe...
So, and then we have one last slide, probably the coolest slide you'll find on this slide deck, because we have screenshots of Snapchat, we have emojis, and we have lots of things happening there. I'm not sure if probably you don't, I suppose you don't read Norwegian, but the thing is that the text what says there is that when you have 1 GB of RAM and create 16 gigs of swap to make things compile, this is what happens. So you can see there, like memory 1 GB, swap 16 gigs. That was this thing of trying to compile a C library on a tiny little device. What we realized later is that that was wrong. I mean, we were not supposed to compile it on the device. We could do that later on. And also that, well, we probably should have upgraded some libraries and stuff like that. But the thing is, the point is, was it a really smooth sailing for us playing around with this thing for, well, last few months? And the question is that, well, it might have looked like this now. In reality, it was a little bit like this. So a little bit cloudy, thunderstormy, wavy, you know, things were like this. And then we got like this. Like, you know, asking support, asking people, asking things, and asking... on Stack Overflow, and the answer got in like 3 months later. So what after that, we kind of learned a lot of things. We played around. We got to some kind of a level where we knew how things were working, and it got to like smooth-ish sailing. But the thing is, I mean, we're not really experts at this kind of stuff. I mean, we work with cloud, we work with Java. We actually do. This is not the thing we do, fortunately, I guess, for living. But so we're still noobs. But well, this is how we got. This is how far we got, and we have a tiny little demo here. You want to see the demo? Yeah, yay. Woo. Okay. So the demo is not very optimized for like lots of lights and people being far and looking at things, and well, you know, and you have a demo effect. So we are doing another thing that you're not supposed to do ever, is to switch computers in a demo. We do that for you again, so you don't have to. So the computer is just doing, basically, is showing the screen, and it has, yeah, we can do that. I guess we'll need, no, we can't. Well, for now we can. Wait, just leave it. So what we can do is that here we're just starting our people count detect server thingy with the different labels and what kind of model we're using and what the threshold. So here we're using 80% threshold. And we also add print at the end. It will be very verbose. So it will add a lot of print statements and stuff like that. So I think we could go back, yes. So, oh shit. Okay. Clear, run. So whenever the server is up and running, because there is also some streaming involved here, so we're actually streaming locally, but to a web page here. Hey, it's me. So let's see if we can actually get it pointing at people. What happened? Demo happened. Good. Touching open electronics with bare, sweaty fingers is a very good idea, always. Well, I mean, you saw it, right? You saw it worked, right? Yeah, we can try to do that. I don't know what. I really don't know what happened. We can, if everything fails, we can always reboot this thing, but it will take some time to boot that up again. We still have 5 minutes for questions and stuff like that. So I think, can you see if there is any questions coming in? I don't know if you can hear that, but there is a fan. It gets really warm. So let's see if we can connect to this thing. Not yet. Not yet. Oh, come on. Oh, now it should be. All right. Drum roll, please. Hey! Okay, now we can try to point it at people.
You can just maybe walk closer.
I don't know. I don't dare walking. Well, okay. Look, it finds people. She's a person as well.
That's good.
And we have the sound.
I think it's too much light.
It's too much light. It's killing the thing. But well, it's not supposed to be working in this environments, right? And it's totally different. It's been trained to work in a different ways and blah blah blah. But the thing is that the point is to put that kind of camera on, like pointing down at a corridor or something like that, and then you will see the people passing by. So you don't really even have to see faces of people for it to recognize if it's a person or not. All right. So I think we will be switching back to. It was a very quick demo, but it worked finally. I think I answered the first question. Oh, no, sure. You cannot see the questions. Let me see. What's happening? There, okay. So the first question is how TPUs are cooling comparing to CPUs. Well, you heard that fan, right? Yeah. The thing is that it actually, as you could see on the picture, it has a separate fan. And the hardware, apart from the TPU part, is more or less the same as a Raspberry Pi 3, and Raspberry Pi 3 doesn't have to have a fan to be cool. That one has to have it, and you will hear it from time to time. Not always, but you'll hear it from time to time. So, you know, it's a bit more, it makes a bit more warmth, but it still is quite quiet. How much all components cost you? What about libraries and all the, yes. So the components, everything, I think, the device itself is $150 and the camera is $50, so $200 in total. A few more cables and chargers that you have for your mobile phones and stuff, so you don't have to pay for that. the libraries are
Free, I think.
are free. They are most of the libraries that we're using come with the device. I mean, you can download them from Google Coral website, and the one that we're using for tracking is called dlib, that you will most likely have to build yourself because you'll be running on an ARM device, so it's not pre-compiled for that. But it's also free and it's available, and it is a bit pain to compile, just so that being said. We have 1 minute and 30 seconds. Any other questions? No? So, okay, we'll be here after the presentation, and this is us. Yeah, we can go full screen, but I don't think we need to. Okay, yeah, good. So, well, this is us. We would love to chat with you and share more of our experiences. Find us here, outside, anywhere. We're going to stay here for the rest of the day. Ping us on the social media. This is Twitter handles. We also have a bit more traditional ones like email and stuff. We can give that as well. It's also social media, I think. It's just the old one, old school. Okay. At least some people claim that. Well, anyway, thank you all for coming, and, well, enjoy the rest of the day.